Get started. So, as someone pointed out, today is our last lecture for like the regular program classes, and we'll do a discussion on Friday on 2 imitation learning papers. But let's kind of do a little recap, and then we'll talk a little bit more about policy gradient and some model-based learning. So, you said that the goal of sequential decision making was this problem. So, you have an agent that they track in the world, observes the state, decides to take an action using a policy, obtains a reward, and then your goal is to find a policy that maximizes the expected sum of rewards. This is almost always the goal in reinforcement learning or imitation learning problems. And we said to solve this, there's 3 different ways of doing it. Model-free RL, model-based RL, and imitation learning. We covered imitation learning 2 lectures ago. We talked a little bit about model-free RL last time, and today we'll talk a little bit about model-based RL. So let's recap what we said. So for policy gradient, the goal is just to take this objective, the expected sum of rewards under your policy, and to do gradient descent on it. And so I want to do gradient descent on it. What makes it hard? Or not just like any other supervised learning problem. Yeah.
So your policy like it's like the actual perspective.
Right. Exactly. So it's the thing that you're taking expectation with respect to. It's not inside the expectation. And so you're trying to solve problems like this, where it's x is drawn from p sub theta of x, whereas supervised learning has the theta inside. Right? So if you have the theta inside, this gradient goes all the way inside. It's like you average gradients, whereas the theta is in the distribution, you have to do this like policy gradient stuff. And so that's what makes these problems different. And so we went through some math, but basically you start from this expected sum of rewards objective. You try to take its gradient. You then move the gradient inside, multiply and divide by p theta, and then use the chain rule. And this becomes an expectation again, right? And so we went through these steps, but to show that when you have the expected sum of rewards and you take the gradient is also an expectation. And the gradient is the expectation of grad log pi or grad log p times reward. Then this is what you call your reinforced trick or policy gradient. And then we kind of like work through a little bit of algebra to show that you can kind of simplify this grad log p into the sum of grad log pi. Right, so the way to get it is you expand p as the product of p of the initial state times the policy times the dynamics times the policy times the dynamics, and then you take the gradient of that thing, right? And you can show that it's the sum of grad log pi. And so the objective that you would optimize at the end is something that looks like this. Everything is computable. Reward is given to you. You know pi theta, so you can get grad log pi. And so overall, this is all something you can implement with PyTorch, right? If you want to implement with PyTorch, you kind of like get pi theta, take log of that, and then try to take the gradient of that, multiply it by the sum of rewards. And so you can approximate this with samples, and so something you can easily implement as code. So when you implement it as code, it kind of intuitively looks something like this. You draw a bunch of samples on trajectories that have high return. You increase the likelihood of the action. On trajectories that have low return, you decrease the likelihood of the action. But the important thing here is that you're doing it on policy. So you draw things from your current policy and then reweight things for the next step, right? And the second thing is that you're going to weight things not by your reward now, it's by your sum of rewards from now till the end of the trajectory. That's including everything that'll happen in the future. So it's important because each action doesn't just affect itself, it affects everything that happens in the future. Okay, that's policy gradient, right? So the objective looks something like that. You have a sum over grad log pi times sum over r. So you have to be a little bit careful here, but it's essentially there's like brackets here. So it's like you take the grad log pi's and you sum up the grad log pi's, and then you take the r's and you sum up the r's, and then you multiply those two sums. So it's not like a nested, it's like two, like use the parentheses carefully. I should probably change that. Okay, that's policy gradient. Any questions about policy gradient? The idea is you draw a bunch of samples, you see what rewards were in each trajectory, upweight things that have high reward, downweight things that have low reward. That's it. Questions? Make sense? Okay. So policy gradient, nobody uses policy gradient in practice. And The reason is that it's challenging to use it in practice because you have a high variance problem. And so the way to understand variance is that you kind of have like a single sample estimate. Let's say if you look at this objective, what that means is that every grad log pi is only weighted by the sum of rewards in that particular trajectory, right? So really what happens is that this, like the actions that you took from here to here are upweighted based on what happens in the future, right? And so like the fate of this guy is coupled to the fate of all these other guys, right? And so if I like have the environment being stochastic and I get unlucky, or if I like have my policy sampling something that's bad, like this action, which is actually good, will get labeled as bad, right? And so the tricky part is that what you really want is something that looks more like that, right? So you want to say that like I took an action and then I want to take many possible futures and like average how good those futures are. But what happens is that you can only take a single sample estimate. So you can only see what happened in your current trajectory, which makes it really susceptible to like noise in your environment or really susceptible to bad samples, right? And so this kind of like makes it hard to use in practice. So this often when you think of why policy gradient is hard to use is because it's a single sample estimate which just says use the rewards in your current trajectory, right? And that's hard to do this kind of thing. And so the solution here is that if you take a lot of samples, right? Like you'll hope that you get like many such trajectories, and then eventually you'll reduce variance, right? So you'll reduce variance of like whether this is a good action or not. The trouble is that you have to take a lot of samples. Whenever you use policy gradient algorithms, including PPO, you typically have a huge batch size. And so you have lots of parallel environments, huge batch size because you have a big variance problem. And so by variance, what we mean is that like you run the algorithm 5 different times, I'll give you 5 different solutions. And so like high variance. So like you can think of the gradient as being noisy. It takes you this way, and it takes you this way, it takes you this way. Just because like in the limit of infinite samples, it will be correct, but you have the n that you have to take is larger and larger and larger to be accurate. All right. So we have one problem, which is that we have a single sample estimate. The other problem is that let's say we considered an action in the middle of the trajectory. The fate, if you look at this objective, right, it's the sum of grad log pi in the whole trajectory times the sum of rewards in the whole trajectory, which means that the fate of this guy is coupled to all the stuff in the future and all the stuff in the past, right? But if I'm taking this action, it's not going to affect anything in the past. I can only affect things in the future, right? And so the point here is that I'm unnecessarily tying my fate of this action to stuff in the past when I don't really need to, right? And so you're adding even more variance. Like you might accidentally have a bad action over here, gives you a -100 reward, even if this thing was pretty good, right? And so you're introducing even more variance. Okay, so the challenge with policy gradient is always variance, and you're going to try and think of ways to reduce variance. Okay. So, first idea that people use is a simple one. It's saying that you like use the fact that your environment is Markovian. Like if your environment is Markovian, that means the current action cannot affect the past, right? And there's causality. I mean, in general, the current action cannot affect the past. You can only affect the future, right? And so normally the policy gradient, you can see it kind of has a sum of t equal to 0 to t and a sum of t equal to 0 to t of reward, right? Now, the problem is that this sum includes t primes, which are less than the t's here, right? So you're saying the grad log pi at some time step, let's say t is equal to 5, will also include the sum of rewards for 0, 1, 2, 3, 4. Because I don't like, but those things I can't affect. I really shouldn't be considering them, right? And so the simple change that folks make is rather than considering the return of a whole trajectory, right? Right now it's happening, you're taking grad log pi's, weighting it by the sum of rewards of the whole trajectory. What we do instead is we just ignore the past, right? You can show that it's unbiased. You can show that it's the same objective. The logic is basically just the present cannot affect the past. And so all you do here is that instead of summing from 0 to t, you sum from small t to capital T. Right, so now the brackets work differently. Like the brackets would be like that. Then there's a small bracket inside like that. So it nested brackets, right? Remember here it's not nested. Here it's this. And here it's nested. Right, so then it's like for every grad log pi, you only consider sum of r's in the future. So you will have like grad log pi a0 given s0, and then you have sum of all the rewards from t equal to 0 to t. But then you'll have grad log pi a1 given s1, and you'll have sum of rewards only from t equal to 1 to capital T. Right? And so you only consider things in the future. And the nice part about that is it like unhitches you from the past, right? And so you only consider return to go, and you do not consider all of the things that are in the past. So that reduces variance. Questions? Does that make sense? Just use return to go rather than return. Whenever you're implementing policy gradient, you like try to only compute rewards in the future. Don't care about it. So the second question we ask is like, can we reduce variance even further? And this is an idea called a baseline. And to kind of illustrate this idea, let's look at a simple example, right? So we'll have like trajectory likelihoods on the x-axis, and we'll have rewards on the y-axis, okay? And so let's say we like have our trajectory distribution that looks something like this, right? So let's say like there's a Gaussian, your trajectory distribution samples Gaussians with this mean and some variance, right? And you drew like 3 samples. So in these 3 samples, the height indicates the reward, right? And so the reward here is like a little positive and the reward here is pretty negative, right? And so this is one sample. So you draw a set of samples from this distribution. Let's say you drew one sample here, one sample here, one sample here, and these are the rewards that you got. Like, so the way to interpret this is like points on the x-axis are which trajectory you drew, and they're like these yellow lines tell you the reward, right? And so if I did policy gradient with these guys, how would the distribution of trajectory shift? This was my old distribution. Now I'm going to do this reweighted thing. I'm going to increase the likelihood of good things and decrease the likelihood of bad things. How does the trajectory shift here? Right. So it like moves over something like this, right? And so you can see that it's going to move over something like that. Now, let's consider a scenario where you draw a different, like you had a different set of samples, which looks something like this, right? So you can see that the difference between those samples is kind of the same. You just added a scalar to your reward. Everything got shifted up, right? But if you look at how the distribution shifts here, it's kind of different, right? So if you look at this distribution versus this distribution, like they're pretty different, right? And so it's like, even if you have rewards that are like, and in the limit of infinite samples, this wouldn't happen. So when you have a small number of samples and your scale is not centered, like some things can lead to bigger increases and some things lead to smaller increases. And so even in the like basically across different states, you might have different scales of rewards. And the things that have large scale might affect things differently than things that have small scale, even though the like net impact on the policy should be the same, right? Because all you care about is how much better are you at doing this than the other things, right? And so in order to kind of normalize this, you use something called a baseline, which tries to center your rewards. So like everything is on the same scale. And so the idea of a baseline is that you're going to do the same type of like nested summation, but you're just going to subtract a function b of st. Right? So it's important that it's like any function, but it's important that it only depends on st and not on action and not on future states. And so the idea is that you're going to take your sum of rewards and you can think of this as like a centering term. It's like a state-dependent centering term, which tries to bring all the magnitude of the gradient to be the same across all different states. Right? And so you'll often learn this function, but it's any function of state, which is kind of like, you can kind of think of it as like a average of the future rewards. It kind of like centers, so you'll compute the average and then you'll say some things are better than the average, some things are worse than the average, but it like centers your rewards. And so you can show that this is unbiased. So you can show that if you actually compute um, this objective, you compute the gradient of this objective, or rather you look at the gradient, it remains the same as the original policy gradient. So you can show that this objective gives you the same gradient in the limit as like just grad log pi times sum of r. So like this doesn't affect the gradient. We're not going to go through that today. It's a bit involved, but if you want to look at it, look at my RL class. There's a big set of slides on it. But the idea here is very simple. Like we made two changes. The first one is we only go in the future, and the second one is we like add something to like center the rewards. And when we typically do this in practice, you often just use a neural net, which maps from state to a scalar. Right? So you have a neural net that maps from some RS to R1. So it takes something that is input is a state and outputs a scalar. Right? And so you train this, often what you'll do is you'll train this to match the average rewards. So like this is a typo, sorry. This is B of ST. You kind of like regress from B of ST to the sum of rewards in the future. And so the point is that your B of ST kind of becomes your average reward. And typically you'll use your baseline as an average reward. You can kind of think of it as you take all your trajectories, you compute the average sum of rewards, and then you regress to that. And so you get something that centers everything. So that's the concept of a baseline. And this allows you to like reduce variance. The critic is the baseline. Yeah. So typically the critic is the baseline. This thing is often called the critic. Okay, so we made two changes to policy gradient. We started by first like reducing variance by uncoupling the fate of the future from the past. And the second thing is we changed the objective to center the rewards, and that reduces variance. And so like most modern implementations will have those two changes made. But that's still not used in practice, right? And so one thing that people found is that like policy gradient is kind of like walking on a ridge, right? It's like you're collecting data, you're taking a gradient step, you're collecting data, you're taking a gradient step. And so if you take too big of a gradient step, you like fall off the ridge, which means that you start doing poorly, which means that your data is bad and you end up never recovering. And so if you just do policy gradient like we did so far, sometimes you'll take too big of a step, and then you'll never improve. Or you have to reduce your step size to such a small limit that it's like extremely slow. Right. And so in practice, what people end up doing is a modification to this called proximal policy optimization, or PPO. And so what PPO essentially does is it says that like, it's a similar objective. You're trying to like increase the advantage, or like you're trying to like move in the direction of the advantage, but you're clipping it so that your policy doesn't move too much. Right. So you're trying to still construct something that looks like grad log pi times advantage, but you're clipping your policies so that they don't move a lot. And what that means, so you're clipping them with this epsilon term. And what that means is that it will not allow the policy to move more than epsilon away from the current policy, right? And so that like, you can kind of think of it as like, there's a ball around the current policy, and the policy is restricted to move this much. You draw more samples here, and then you have a ball around this policy, it's restricted, but it doesn't ever let it like take these extra big steps, right? And so the big change from policy gradient to PPO is just like this kind of clipping term, which forces your policy to not change too much. Right? And so you want to go in the direction of like maximizing advantage, but you want to do it in a way that doesn't move too much from the current policy. That's the main change in PPO. And so the nice part about this is that it allows you to take more gradient steps and have more stable updates without this. Sometimes if you implement policy gradient, you'll see that it like does well and then suddenly stops doing well, and then does well and then like forgets everything. And like that kind of thing doesn't happen with PPO as much. Okay. So we looked at some of the last time. We did some implementations of PPO. Like all of these use essentially PPO. Good. So the advantage term, you can kind of like draw it from here, right? So if you think of your value function as the average reward, right? So your value function is your average reward under your current policy. Your advantage is telling you how much better is your current trajectory than your average. Right? So it's like my average is here and my like current trajectory is here. It's telling me what is the gap between the average and my current trajectory. Right? So it's like it's rather than an absolute number, it's like a relative number compared to the average. Right? So it's like the problem is that the value function at some states can be 1,000 and other states can be 0. Right? When you put everything into advantage space, everything is like in the same scale. Alrighty. So there's some examples there. The same algorithms were used in RLHF. And then finally, we talked a little bit about these robotics experiments. So these robotics experiments don't actually use PPO. They use a different algorithm called SAC. And the way that these SAC algorithms work is that they're like PPO, but they do dynamic programming. And so like what PPO is doing right now is computing the sum of rewards in a single trajectory and then like subtracting a baseline. What dynamic programming does is it tries to like if you remember how LQR worked, we started going from the back, right? Dynamic programming tries to build a more efficient way of like constructing these like advantages by using dynamic programming. We won't have enough time to go into the details, but the nice part about these algorithms is that while PPO only uses the latest data, or policy gain only uses the latest data, this allows you to use all of your past data, even if it's not coming from your current policy. And so the nice thing about these algorithms is that you can use them with all of your past data, data from other experiments, data from experts or demonstrators. And so that makes this more efficient. And so this is often called off-policy RL. It's worth like 3 lectures of material. And so you guys should look at my deep RL class. It covers a bunch of this. Or take a next year. But we'll move on to model-based RL. And so a recap of policy gradient, we started by just taking doing gradient descent. We said it's high variance. We made 2 changes using the return to go and the baseline. And then you made another change, which is like, don't let the policy move too much. And that's what gives you PPO. Does it make sense? Okay. That being said, let's move on to model-based RL. So we've already covered a bunch of model-based RL. So we'll skip through some parts of this. But the premise of model-based RL is that let's not try to learn a policy. Let's instead try to figure out a model of how the world works and then use that model to decide how to make decisions, right? And so if you remember, we did optimal control where we knew the model. And now we're in reinforcement learning where we don't know the model. We can just get samples from it, right? And so the premise of model-based RL is you're going to like try and learn a copy of the environment, learn our best approximation to the environment, and then use that to make decisions in the world, right? And so the thought is that instead of trying to like assume that the environment is known, let's just collect data in the world, try to learn a surrogate model of the dynamics, like learn an approximation of the dynamics, and then use that to make decisions, right? So like, don't make decisions against your like true environment, make decisions against your estimated environment, right? But the nice part about it is that it's a model, so you can do whatever you want with it, right? And so you can generate as much data as you want, and that data is free, as opposed to data that is coming from the real model, right? And so it's 2 steps as opposed to policy gradient. Policy gradient just like tries to do trial and error directly in the environment. Whereas what model-based RL does is it first tries to build a surrogate model, do some improvement in there, go try those things out, then improve its surrogate model and repeat, right? And so the key premise here is this like learning how the world works. Like you often hear the terms world model or intuitive physics or these kinds of things for model-based RL, but it's all the same idea. Okay, so you learn how the world works first, and then you use that to like make decisions. So why do we want to do this? Why would we ever want to learn how the world works to make decisions? I only care about decisions. Yeah. I would actually expect that in a really complex environment, modeling how it works is really hard. So I would expect that decision making might be even easier than modeling. But maybe to flip it, maybe in really simple environments, like modeling might be easy and they might be easier than learning a policy. Other thoughts? Yeah.
Maybe with a model, you could plan further in the future and then take some optimal options for actions like get more.
Yeah, so I think that's true in principle. It gets tricky in practice because models have compounding error, like they get worse over time. But if you could do it perfectly, then that would be good. Some reasons I thought of, one of them is that you can transfer. Like if you learn how the world works, it's agnostic of what problem you're doing. Right? Like you're just understanding how the world works. And once you understand how the world works, then you make decisions on whatever you want. You like can open this or push this around or turn it over. And so it's essentially extremely transferable. It's often really, really efficient. Like this plot kind of shows model-based RL. You can't even see it, but model-based RL is this guy, and model-free RL is these guys. Right? So it's like extremely efficient often, compared to policy gradient. Lower variance, it tends to learn a lot quicker. And the last reason is that it's really simple, right? It's just basically doing supervised learning, which makes it really simple, which means you can apply your favorite like deep learning tricks to it. And you can have a big transformer model, or you can have whatever, a big diffusion model, like anything that's in deep learning will transfer to model-based RF. And I think that transfer is probably the most important bit, but each of these matter in different ways. So here's an example of model-based RL in action. This is a robot learning to like rotate these balls in hand, just with real world experience. And so this is like maybe under 2 hours of training. But you learn to like manipulate these things with like a high degree of freedom robot hand, like with zero simulation data, all real world data. So it's super efficient. It can be effective on high dimensional systems. So let's learn how we do it. The problem statement is that we're going to do model learning, which means we're going to collect a bunch of data from the environment and learn a surrogate model. And essentially, to learn a surrogate model, you optimize an objective that looks something like this, saying that we define some loss function, we collect some data set from the world, and we try to find a surrogate model p theta hat that best approximates that data. Right? And so it's like, you can kind of think of this as supervised learning. It's just doing supervised learning on the environment. Now, once you have a model, then you can do what you often refer to as planning, right? And planning just means that in your model, you're gonna figure out what decisions are optimal, right? And so if you remember how we did optimal control, we did MPPI and these kinds of algorithms, they're basically planning methods that like decide how to act in the world. Right? And so planning essentially will solve some sort of reward maximization problem, right? But the important bit here is that it's not under the true dynamics of the world, it's under p hat. The first step is infer p hat from data, and the second step is do reward maximization inside p hat, right? And then you alternate between the two. And so the nice thing about planning is that you don't always have to learn a policy. You can also figure out just a sequence of actions that are good. It's just different algorithms do different things. And so the question becomes, these things feel reasonable at an abstract level. How do we instantiate them concretely? Right? So we're going to try and use neural networks as our models. So we'll try to have like some sort of rich function approximator that goes from state and action to next state. And then we'll try to solve these two problems in the context of learning neural network models. So both of these are learning neural network models. This one's from Byron a long time ago, and that one's from Manusha. And both of them learn neural network models with small amounts of data and then use them for like highly dexterous or high-speed tasks. Cool. So the assumptions we're going to make, just to be formal, is that we can only sample from the dynamics in the true environment. You don't have access to it. You can reset the environment, so you keep getting samples from the same place, and you know the reward function, right? In model-free RL, you didn't assume that the reward function was known. In model-based RL, let's assume that the reward function is known. And a basic template kind of looks something like this. You start by collecting some amount of data. You then learn a model from that data, use the thing to plan, and go collect more data in the world, update your model, replan, update your model, replan, and so on, right? And so we're going to try and instantiate this in different ways. So there's five different versions we'll cover, but I think you guys have already covered 0 and 1, so we'll skip through those quickly. But 3, 4, and 5 are more, or 2, 3, and 4 are more. Okay, so we'll start with random shooting and MPC, go to MPPI, then add in uncertainty, then add in policy optimization, and go to images. So to start, the simplest algorithm we can use is just do maximum likelihood, right? So you're trying to learn a model of the world. The model of the world takes in your current state, your current action, and predicts the next state. And you're just trying to do supervised learning. So you collect data from the environment, you try to do supervised learning, and then that gives you your model. Right? And for planning, you just do random search. So we've talked about this in optimal control. You just try random actions, choose the best one, execute it, try random actions again. And I think you guys did it in your homework also. The simplest version of this is to do like a regression problem, but you can also have more complicated versions of this, right? So if you used p hat theta as a Gaussian, then this like maximum likelihood problem reduces to regression. Right? And so you can show that like basically if p hat theta is a Gaussian, then this thing would be like a regression between f of SA and like S prime. You can kind of do the same thing for other model classes. So if you have a p hat theta being we call an energy-based model, you get an algorithm like contrastive divergence. If you have p hat theta being like a diffusion model, then you get something that you call core matchup. And so different choices of p hat theta lead to different algorithms to train these models, right? But they're all essentially supervised learning. Once you've trained the model, what you have to do is you have to do planning, right? So you have to decide what actions to take in the world. And so the simplest thing you can do is just do random search, right? Just try a bunch of random stuff, choose the best one, and execute it. And we've talked about how this is a bad idea. Why is it a bad idea? If I just basically chose random actions, I learned my model with supervised learning, and then I just tried random actions in this environment, right? So I tried a bunch of random actions. I chose the trajectory with the highest reward, and I executed all the actions.
Oh, because you're basically taking that, or you're gonna simplify the
Right.
record.
So yeah, there's this like needle in a haystack problem. So that's one problem. The second problem is that it's like if your model is wrong, which is almost certainly going to be, then these actions are likely going to be wrong. And if you just play them open loop, there's no way for feedback to ever correct your model. Right? And so doing random search is usually fine, but when your model is pretty wrong, executing actions open loop is not a good idea. Right? You've probably seen this in your controls homework too. So we talked about model predictive control earlier, right? So model predictive control just says don't execute your actions open loop. Instead, when you execute your actions, keep replanning. So you like execute your actions, you go one step, then you replan, then you go one step, then you replan, then you go one step and you replan, right? And so the nice part about replanning is that you kind of give your model opportunity to correct its errors, right? So this is often what you call model predictive or receding horizon control, right? You can kind of think of it as like the horizon is changing every time, right? And so often this matters a lot with learned models because learned models are more wrong, right? Learned models are only good in a certain region. And so you really need to replan because sometimes you'll make mistakes. And so when you have a learned model, you plan with random shooting, you choose the best sequence, execute the first action, and then you repeat. Right? So the overall algorithm looks something like this. You start by doing data collection, you learn a model with supervised learning, then you do planning under the learned model. So here you're going to just like stick it into your p hat theta and kind of like hallucinate the future. You pick the best hallucinated future, execute the first action, and you repeat, right? And you measure how good the futures are by your known reward function. Okay. So that's the simplest version of model-based RL, that you learn a model, you execute things in the world, and then you replan. Does it kind of work? Or does it work? It kind of works. Like some things in simulation seem to work. There's a few examples in the real world. I might have showed you guys these examples earlier, but I think they kind of are compelling because it's just learned with like a few minutes of real world data in both cases, and you can learn or you can plan to do different tasks just with the same model. So the challenge with these kinds of methods is that there's still a significant gap between how well these model-based RL methods do and like the maximum performance. Yeah, go ahead. Good question. So usually what you'll do is you'll collect a bunch of data, you'll learn your model once in batch mode, then you like keep doing replanning, where you don't update the model. You just do replanning to collect a bunch of to like execute things in the world, and you take all of that data and then you fine-tune your model from there. Right? So it's like you never start from scratch and you never learn the model in the middle of planning. You learn it after. Right? Good question. Sometimes you'll have like an asynchronous loop where you like collect data and it's like updating the model in an asynchronous way. But most people will often do this batch, like they'll train a model, collect a bunch of data of the model, then improve the model, then collect a bunch of data. So the challenge is there's a significant gap between how good model-based RL does in green and like the max reward of the task. So like this MPC loop is still not like maxing out performance, especially for high dimensional systems. And so the solution is something we've already talked about before, which is solving this needle in a haystack problem. And it's saying that like in any high dimensional system, random actions are unlikely to chance on the goal. So let's have a smarter method. And so we talked about MPPI, right? And the idea of MPPI is that you can try to like do sampling towards things that already give you high reward, right? And so rather than just doing random sampling every time, in MPPI, you sample a bunch of stuff, you see which stuff give you high rewards, and you sample more around there, see what stuff give you high reward, and you keep increasing the likelihood of high reward things. And so essentially what MPPI does is it samples a bunch of actions, puts them forward through the model, reweights them according to the reward in those trajectories, and then resamples, right? And so essentially you can kind of think of it as this thing on the right. You drew some samples, you saw the green was the best thing. Then the next time you draw samples much closer to green, right? Rather than all over the place. And so it gives you like a lot better performance generally. And the loop kind of looks similar now. The only difference is in this planning part. Earlier, what we were doing was we were just throwing out random actions, and we were like choosing one and then repeating, right? Now, what we do in MPPI is you throw out random actions, you find the best one, then you do random actions again, then you find the best one, and you say repeat this process k times, right? And that gives you the best trajectory that you then execute. So like your planning step is more complicated because you do multiple rounds. So what's the con of doing that? Like, why shouldn't we do that all the time? Seems like it's kind of like reasoning, right? More steps are better. Yeah. Yeah, definitely susceptible to local minima. The other thing is speed, right? Like you want a real-time system, you want a robot drifting at high speed. You can't like spend hours and hours and hours doing planning, right? So lots of folks have been thinking about GPU parallelizing and PPI and these kinds of things, but it can often be slow. That's what makes it hard. Um, so MPPI is the algorithm that they use to like kind of do some of these drifting tasks here. And here they're doing like, I don't know if they're doing onboard compute or compute in that tent, but it's like able to run pretty fast, which is nice. And so you can kind of see like this thing at the bottom shows you like the planning kind of. You can see like those are the proposed trajectories and you pick the best one. That's things that we've already kind of covered. Right? But what makes model-based RL unique is the fact that you have learned models. Right? And so if you have learned models, the issue is that rollouts under your learned model may not be equal to rollouts under your true model. It's kind of like imitation learning, right? You like have this kind of compounding error problem. So let's say this is your true rollout. And if you have a model, what will happen is that you have the true rollout and the predicted rollout kind of deviating. And the same issue, like you make a small mistake at the first step, it goes into your model, it's OOD. You make a bigger mistake, it's more OOD, it's more OOD, it's more OOD. So your model and your real world start to diverge because you're like predicting things auto-regressively. You feed your predictions back into your model and repeat. Question? No. So the challenge is that you have this kind of compounding error in places where you just don't have data, right? So imagine that you like made a little mistake and you went like a little bit out of distribution. You don't have data there, so you like kind of predict something crazy, right? And so if you ever look at these video prediction models, they often get blurry. Not recently, but they often get blurry because they go out of distribution and start producing like artifacts because of this compounding error problem. Right. And so the issue is that small errors in state go to OOD next states. OOD next states will produce even more OOD next states. And so you'll have your model being bad on things that are out of distribution. Right? This is not a problem in a true model because the true model is not a learned model. It doesn't have any notion of in distribution and out of distribution. it only matters for learned models, right? So learned models are basically only good in a certain region. And when you start to go outside that region, they produce bogus. And so what makes model-based RL challenging is this compounding error problem. And that's why most learned models don't plan over huge horizons. They plan over just a few steps. And so how could we deal with this kind of compounding error? Any ideas? Yeah.
Like do the same type of like dagger. I guess like populate data set with.
Exactly, right. You could try and like roll things out. Um, you can try and roll things out and see like where things went wrong and then provide some corrective labels back. Turns out that actually optimizing that like becomes pretty hard. And so empirically, people haven't found a lot of success with trying to get models to not have compounding error that way with like, so a good paper to read is called Data as Demonstrator or Data as a Demonstrator. And it kind of tries to do this idea of going back. But often what happens is that it becomes a harder optimization problem. And so instead, what folks often do is that you measure uncertainty and you use that to influence your planning. So the key idea here is that when you like go to this region, if I'm able to measure uncertainty, I can kind of know that this thing is hallucinated, it's not real, and then I don't consider it in my planning, right? And so one of the big changes that folks did for model-based RL is that with maximum likelihood models, you just go out of distribution, but you pretend that it's the truth. With uncertainty-aware models, you're able to know when you're out of distribution. And if you know when you're out of distribution, you can like avoid those behaviors. And so, how much time do I have? 5 minutes. So the important bit here is that if we're able to estimate uncertainty, that uncertainty can factor into the decision-making process, and you kind of avoid it, right? So I'm going to avoid the details, but generally you can learn an ensemble of models, and ensembles capture uncertainty. Basically, in regions where you have less data, ensembles differ more, and where you have more data, ensembles differ less, right? And so there's a tractable way to kind of approximate your uncertainty. And what we do with that uncertainty then is that instead of taking the expected rewards when planning under your current model, you take it under your uncertain dynamics, right? So you say that you kind of like try to avoid things with high uncertainty. And so you go towards like staying, you tend towards staying in regions which have low uncertainty. And then so you kind of avoid these high uncertainty regions. You want to stay in these regions that have low uncertainty. And you can do that in different ways. One of the ways is to just optimize the expected reward under an ensemble of models. And the idea here is that if you optimize it under all of the ensemble of models, the only thing that will be good is something that is consistent across all of the models. And so you kind of are implicitly told to stay in a region which is low uncertainty. The more explicit way of doing this is like you just penalize it, right? So you're just like optimizing your sum of rewards. I'm sorry, I'm rushing through things. This is our last lecture, so we have to finish it. But you just optimize your sum of rewards and you like penalize any uncertainty, right? So you just in your planning procedure, you say if you're in a region that's uncertain, you've reached a bad set of actions, avoid it. Right? And so if we take these kinds of approaches, that's what is used to build these types of demos. It's a combination of MPPI that we did last section and penalizing these uncertainty things in your model. Yeah. Great question. Often you have the same architecture from different initializations, but some people will like also subsample the data. Some people have different architectures, but often it just works well with just different initializations. And so it works on a variety of problems, but you can't just do MPPI, you also have to add in these uncertainty terms, right? And that is kind of uncertainty-driven models. You calculate uncertainty with an ensemble and you penalize that uncertainty. And that's different in a learned model than it is in a ground truth model, right? So optimal control doesn't usually do that, whereas model-based RL would. Now, one issue we found is that we're doing planning in the loop, which means that it's super duper slow, right? And so when you have tons and tons and tons of samples that you have to take at test time, it becomes really slow. And so the next idea that people looked at was how do we amortize all of this. When I say amortize, I mean like try to use lots of data at training time. And at test time, you have really fast inference, right? And so rather than doing this expensive test time compute thing, you do expensive train time compute and cheap test time compute. And so the idea is to speed up model-based planning by instead of using the model to plan at test time, like we are doing before, we just generate a lot of data from the model and then use that to learn a policy. And so you pretend that your model is a simulator, you learn a bunch of stuff in that simulator, and then at test time, you just deploy the policy that you learned in the simulator, right? And so the key idea here is that instead of using the model at test time, use the model at training time to generate lots of data. You learn a policy, which is a feed forward thing that goes from images or states to actions. And then at test time, you just deploy the policy. So at test time, you don't have to do this expensive MPPI loop or anything. At test time, you just run your policy forward. Right? And so the nice part about that is that it's efficient at test time, right? So your procedure looks something like this. At training time, you learn some models, you generate data from these models, put it into a buffer to train something like RL, right? You get a policy that you can then deploy in the environment. But the important bit is that your rollout in your environment is not some planning loop, it's just a policy. So it's like much more efficient, right? And so if you do that kind of thing, you can get behavior that looks kind of like this, right? And so there's an example from some folks at Berkeley, but you can do much like normally if you see how MPPI works on these systems, it's like much slower. It like kind of goes pretty slowly, whereas here you're able to collect data and learn pretty quickly, like within 10 to 15 minutes of experience, but you're able to operate at real time. You're not like really slow, right? Which is nice. And we have 3 minutes. All right. So the key idea here is encapsulated here, perhaps, which is saying collect a bunch of data, learn your models, instead of doing planning at test time, generate a bunch of data, use it to learn a policy, and then go back to collecting more data with your policy, right? And so the model is used at training time rather than test time. The last idea we'll cover is how do we go from these low dimensional states, like where the joints are of your robot, to images, right? And so when we want to go to images for these kinds of problems, how do we go to higher dimensional state spaces? And the idea here is to use latent space models. We won't cover them in detail, but it's kind of like filtering, right? You're trying to figure out a latent space from your observations and then do planning in that latent space. And so there's a bunch of algorithms where you can learn latent spaces, right? So you can learn a latent space that best captures the dynamics of the world and then plan in that latent space, right? So we'll skip the details, but some examples here are like some people played Minecraft, which is inherently a pixelated image-based thing. And there's the first ones to like figure out how to mine diamonds, the thing, right? And it tends to be super duper efficient, which is nice. And so you can kind of get it to learn robot behavior in the real world too. So you can learn to like, pick and place objects, move things around, have a robot learn to walk in just a few minutes of experience directly from vision, right? Which is nice. And so that's kind of a overall picture of model-based RL. We started from random shooting. We added MPPI. We then added uncertainty. We made it faster by generating data at training time. And then you can extend it with latent spaces to work from images. Cool. All right. I think that's time. Maybe a little bit of perspective on model-based RL is that, I think other types of algorithms will get more efficient and other types of algorithms will figure out the tricks, but like model-based RL will continue to be transferable. So if you're trying to do model-based RL, I would focus on how to make the same model work across many, many, many problems. That's where the generality comes. Okay, I think that's it for me. I'll see you guys on Friday for the seated discussion. But yeah, it's a pleasure. Thanks. That's all.